go and talk about symbolic-numeric certification of overdetermined and singular polynomial systems.
Thank you very much for the invitation. Yes, so this is a work in collaboration. Parts of the work is in collaboration with one of my students. She's a lady from Turkey, John Howenstein, who used to be at NC State, but he moved to the University of Notre Dame, Bernard Morin, and Victor Kahn. So the problem that I will talk about is the following. You are given a polynomial system in n variable, and most of the talk I will talk about is that the number of polynomials is larger than the number of variables. And we will assume, and it will be important, that the polynomial system is given over Q. The coefficients are in rational numbers, and we know them exactly. And the other part of the input to this problem is an approximate point, and the goal is to try to certify that this point is nearby, and I will specify what I mean by that in a second, nearby a root of this polynomial system, an exact root. So in the case when the system is a square system, same number of variables and equations, and the root is a simple root, no multiplicities, then there are actually not one method. I will mostly talk about one method in this talk, or mention, I'm not talking about mentioning. Alpha theory gives a tool that you can certify the following property, that Newton's iteration, when you start it from the point, your approximate point z, it quadratically converges to a root of f, and this is what we will call near a root. So this is possible only for square systems with simple roots, and there are other ways to certify the same property. For overdetermined system, and we have more equations, then usually the system do not have a root. So even if it had a root, when you perturb a little bit, it most of the time loses this property of being consistent. So you can talk about several ways of certification. So in the literature I will mention, there is some literature about trying to see whether if you perturb your system a little bit, you will have an exact root near your point. So that is still possible to do using, for example, alpha theory. I'm not going to talk about that. The question that I'm talking about is how to certify if you know exactly your system, so it's a system with rational or integer coefficients, and you want to know that whether that root is near an exact root, like an exact root of your system. You understand the difference between the two questions? So the big difference that this question is not a continuous question. If you perturb your input, the polynomial systems, it's not going to be any more true. So you want to decide a property that is not continuous. So in this decision making somewhere, you will have to make a decision whether a number is exactly 0 or not, this kind of decision. And we will focus on this problem in this talk. So here is a little motivating example that is a conjecture by Littlewood that was confirmed and proven using these root certification method. So the conjecture is the following. You are given 7 infinitely long, or as long as you want, cylinders. Each of them has exactly the same radius, and you want to make a configuration that each of the 7 meets all the other 6. Yeah, and so Bozoki, Lee, and Ronyai was my undergraduate advisor in Hungary, proved this, or constructed and proved this conjecture using the square root certifier, the alpha theory-based root certifier method, and they constructed it. And what they did is the following. They set up a polynomial system, and it was a polynomial system over Z. It was a square system, and they used homotopy method to find all roots. There were millions of roots. They had to follow passes for weeks to get all the roots, and there was a lot of roots. And what they certified, and with alpha theory you can also certify that they had real roots, right? Only the real roots give real examples, and they did it, and they basically proved using all kinds of equivalence methods that there is only two non-equivalent real solution, and this is one, and here this looks like the other one. And
why is the problem interesting?
But it's a nice combinatorial. I think that there is actually earlier research that people were looking at this, whether it's possible, a different setup, or whether you can do it from cigarettes, the short legs, cylinders like cigarette. But yeah, it's just a fun problem. And here is you see, this is the actual, they created it. They created the setup, and this student is interested. Okay, so here in this talk, I probably not gonna have time for everything. I wanna give a lot of stuff. So the first thing I will show you is what I mentioned is simple roots of overdetermined systems. So again, more equations and variables. The second part of the talk will be certifying multiple roots, or I will define what is isosingular roots. We will reduce that into the overdetermined case. And then in the last part, I will talk about a completely new method that also certifies, computes and certifies the multiplicity structure of multiple roots. And I will define what I mean by multiplicity structure. Just before I get to it, the first two, the methods we give are not new. It's just we use it for this purpose. The third one is a completely new method. So the first, as I mentioned, the overdetermined system. So before I get to the overdetermined system, let me kind of motivate it by explaining what is the difficulty there. So, and what we know. So for the square, starting with the square system, so we will use this. We will reduce our case to the square system. And so what alpha theory allows to certify is not only that there is a nearby root, and again, nearby meaning that Newton's method quadratically converges to a root, but also that the corresponding root is a simple root. So that allows actually to certify that you are near a real root for a real system. And also it gives bounds for the distance. And so for for general analytic functions, the formulas in alpha theory would require all derivatives. And for polynomial systems, obviously you don't need that, but actually in a fairly recent paper of Heinstein and Sotai, they gave, I think it's a relaxed formulation. It gives a bound that is very easily computable. They implemented it, and that's what that so-called alpha certified software was used in this little Littlewood conjecture. So it's something that's available, and you can use it. And so as I mentioned, the difficulties with the overdetermined systems, that it's a completely different problem. So first of all, I want to mention that there is an alpha theory by Didier and Schub for overdetermined systems. So what you could certify with that the so-called Gauss-Newton method converges. Similarly, you could use it. But the problem here is that you cannot distinguish between local minimums and actual roots. So that's part of that. So I mean that's not the reason, but we're not going to be able to use it. We're not going to use that alpha theory. And then the other thing I want to mention, which I mentioned already, that you cannot use error in the coefficients I mentioned because you lose the property. Okay, so in this paper that I mentioned earlier, Heinzen and Sotai paper, they actually give a method how to certify that a root or a point is not near. So the answer is no, right? So you're given an approximate point, you can certify with alpha theory that it's not near a root. And the idea is very simple. So you have an overdetermined system, you take two random square systems and you compute all the roots of them. And then you have your point. And your point Z, let's say, is an approximate root for one of the square systems, one root, and another one for the other square system. And you want to see whether these 2 points are the same, right? And basically what they do is that they go close enough such that you can bound this distance, that this distance is the sum of these distances is smaller than when you get closer and closer than the 2 points from each other, and then you know that you are not, then these 2 points are separate and not the same. Yeah? So this direction is the easy direction. And they also talk about how to certify what we want to certify, that you are near a root. And this is the lemma that they give. So basically what it said, that if you have the function which measures the two norms of all the functions, the distance from zero, it's like a real function. Think of this locally. This is 0. So if it's not 0, then there is a positive value that separates it from 0. And in fact, if the original system was a rational system, there are lower bounds for this value, and they propose to use those lower bounds. However, they say it in the paper that these lower bounds are too small to be practical. So let me show you one of these lower bounds. That is, go back to Kenny, that was probably the first such lower bound. This is the case when you have a square system, f1 is to fn, and an extra polynomial, and you want to give a lower bound on that this polynomial is not 0 in a root, then how small can it be? And if you see, this number depends on the degrees of the polynomials and the heights of the coefficients. Heights meaning I think this capital H I used for not the heights, just the absolute value of the coefficients. And the lower bound is double exponentially small. So even the logarithm is exponentially small. And the reason is for that is that this is an example that you cannot really get better. So in the worst case, you can construct systems that this kind of double exponential bounds are achieved. So here is a system, n variables, the polynomials are all quadratic with the coefficients of size 2, or not size, absolute value 2 or less.
So in the theorem, G is any G?
Yeah, any polynomial that doesn't vanish on that point, right?
All right, okay.
Then it has to be, I didn't write it, yeah, sorry. Yes, G, it's not 0 at psi, then it has to be at least that number. And here, so this is such a system, and basically the last coordinate here is double exponentially small. So in these lower ones, you cannot really expect better because they should work for every system. But, so if you look at these papers, I'm sorry, I mentioned actually, GF actually worked on this problem, giving such lower bounds. So if you look at these lower bound papers, they actually, all of them, without exception, reduce the case to the univariate, reduce the problem to the univariate case via methods that are computational methods. These are like resultants or true forms or the things that I was familiar from computational algebra. And so the main idea which come up that why don't we compute those, try to prove that it doesn't cost that much to compute it compared to, let's say, homotopy method, and then just use it and get in the end, use it as a certificate in the end, but you would use then for those now, like you would compute, what we will do is compute an exact square representation and then use alpha theory to certify it. And this is what the whole talk, and it's nothing really new. The algorithm that we give is not new. There's a lot of work, as I mentioned. I don't want to go through everything. So the first part I list is the mention at the beginning, the certification of the continuous properties that we don't do. And here, our method is reconstruction of exact object. And this has been a theme in computational algebraic geometry. This is what they do, but usually using periodic metric and not the Archimedean metric that we have here when you want to turn floating points into rational numbers. But we use exactly the same kind of techniques as like these people here, very similar one. There's a lot of work on use like iterative methods in the periodic or maybe in the multivariate case in the modular metric, but they are iterative. So let me just mention really briefly the algorithm on an example. So here we have 3 equations and 2 variables, and the solutions. This example I will use also for the singular points. So it's the intersection of a circle and a parabola with 2 singular points. So we added this third equation that cuts out basically the Jacobian of the system. So now we have an overdetermined system. So what our method is the following. First we use a homotopy method. Choose some random 2x2 subsystem. I call it subsystem, but you take combinations of the polynomials and solve it. And then you get a very simple system with 4 roots. And then we choose from the 4 roots candidates which satisfy all the 3 polynomials. And this part is the heuristic part in the sense that this is where things can go wrong. Sometimes when they're close to the residues, let's say close to 0, that's where you cannot decide which to put in. But in this case, there was no problem. So these are the 2 approximate roots that are candidates to be the roots here. And so what we do here is we reconstruct what's called a rational univariate representation. So this defines the roots of this component, right? But the difference here is that in the previous slide, no matter how close you go to the roots, you can never find them exactly. This number is an irrational number. This will be 1/4, but this is an irrational number. So in this rational representation, it defines the 2 roots together, but now you have all rational coefficients. So you can actually, using iterations on the roots, you can use basically, it's a Lagrange interpolation, how you get, or even simpler, how you get these polynomials. And then, this is the exact part, you check correctness, that's all. So you construct this so-called rational representation, and then you reduce your original polynomial symbolically, and if you get 0, then you found the rational representation and you're done. And then you can apply alpha certify to certify your roots. So this I'm not going to talk because it's just minor details about this representation that you use, that there are better and worse representations. One is called polynomial, the other is rational. So, but what you can see here is that no matter what you use, this is like a Lagrange interpolation that you need to compute. And this is again the algorithm. This is what's the algorithm. So as I mentioned, we will not always converge. So in this heuristic part, maybe you chose the wrong route. So you converge to something that never gonna be rational, right? For example, if you just converge to the wrong set of roots, maybe just one root, then it's never gonna be rational. So how do you decide that? So this is the hard part. So if you converge and you find it, we prove it, that then everything is nice. You find it in very fast in the input and the out, polynomial in the input plus the output side. If you do not converge, you will be able to terminate using the worst case bounds that I mentioned. So in those cases, you eventually have to use those worst case bounds. So I'm not saying that this algorithm is always better than the worst case algorithm, but most of the cases you will get, it is called early termination. So you will be able to, when you find it, you will know it. So this is what we prove here, that in the when we find it, then very few iteration is needed depending on the heights of the coefficients and how close you were at the beginning. That's how many, basically in the output size, logarithm of the output size, iteration is enough. In the bad case, if we need to use the worst case mind, the number of iteration will be linearly n, but you can think of it that each iteration doubles the number of good digits that you will have to use. So actually the numbers that you will have to compute with will be exponential in n. And this is to summarize these results. And here is what I mentioned with Victor Pan, a little bit of collaboration. We also worked on how would it compare to in parallel to the homotopy method. Can you parallelize this algorithm? And then we worked with Victor Pan to show that this algorithm is very doable. If it succeeds, it's very doable, it's very comparable to the homotopy method, but even better because the homotopy method have to follow all the paths for all roots of a square system. This is gonna be the bottleneck. Once you have an overdetermined system, the number of roots most of the time is much smaller. So the Newton method that we will use will just follow those few roots that we are interested in. So it's really not comparable. So really the bottleneck is the first step of computing all roots of the square system. So, okay, so in the second part, I will talk about how to apply this to the case when we have a square or non-square system, but the root is a root with multiplicity. So in this case, what we will do is a method which certifies approximations to what's called iso-singular points. So I maybe didn't even mention in the previous case, we assumed that all roots were isolated. The system had finitely many roots, all roots were finite. Iso-singular points are points that may be roots of a system that have positive dimensional solution, like here, it's like a surface, but then you and I will describe, deflate the system, then the points that have roots of the deflated system are now isolated. So it's maybe not isolated root of the original system, but once you deflate it, the deflated system will be isolated. So what is this deflation? So what this deflation is what in numerical analysis people use when they have to deal with multiple roots in order to be able to still converge to the root. So there are many different methods. The one that we use here does the following. Sets up the original system, takes the Jacobian, and it takes it symbolically. And it knows you can compute that the Jacobian will have it will have a non-generic rank because there is a singularity there. So it will have subdeterminants which are 0. And here it's easy to prove that you can choose just the subdeterminants that surround a single square non-vanishing subdeterminant. So it's polynomial in many polynomials that you have to add, not all subdeterminant. And you don't increase the number of variables. The number of variables remain the same. And then you do this iteratively, and eventually you get a system which most probably will be overdetermined and will have the original root will still be a root, but with multiplicity 1 now. So this is called the deflation of that root. So, and then you got back to the case that we already handled, that it's an overdetermined system with a single root. Now, before I get back to that example, just want to say that this method is not very efficient if you have to do this multiple times. So the second iteration would be now taking this bigger system, taking the Jacobian of that one, determinants of the Jacobian of this much bigger system, and also the degrees will grow, right? Then you compute this iteratively. The degrees and the number of polynomials in the system grow. So this method works well with 1 or 2 of such iteration, but no more than that.
Do you have some assumption on F? For example, if I don't know whether you said that there's a singular root, so that might be the cause, but if I take F to be a linear system,
Yeah.
And some of these determinants would be units.
But in the linear case, there is no possibility of singular roots because linear system have a single root. Okay. Yes, so this will only, you're right, all the determinants are constants in that case. But in the general case, these determinants will have much higher degree, n times higher degree than in general than the original system. And if you do it iteratively, it will really blow up the degrees of the polynomials. If you do this, taking Jacobians of systems in a row. But anyway, for one step, which in this example, you just have to do one such a deflation. So each of these steps called one step or one iteration of deflation is doable. So here, this is how we got this system. So we started by the intersection of the circle and the parabol, and then you look at the Jacobian and you notice that at these, if you have approximations of these points, you can see that this determinant of the Jacobian is more or less 0, and so you add this the determinant, so it's just a single determinant of the Jacobian. And we already seen how to compute a rational representation and how to certify that. So here is a little bigger example. Here, this is called, this is a system that appeared on similar papers on deflation and multiplicity called Capress system, and it has 24 single root and 8 multiple roots. And these multiple roots, the Jacobian has rank 2, so we add 4 3 by 3 minors of the Jacobian, and then using this method that I described, we get this rational representation for the 8 double roots. And there are other examples that I wrote. So now the third part is the multiplicity structure. How much time I have? 5 minutes? 10? Oh, no, it's more. Okay, because I like this part analysis because this is the newest work we done this. So what I want to mention that in the previous method, with this deflation, you get in the end your original root with multiplicity 1, but you lose completely what was the multiplicity structure of the original system. So this method gives a new system that deflates the original in one step. So you write down one new system and it will be completely deflated, and it will also give you the multiplicity structure. So let me start. What do I mean by multiplicity structure for those who haven't seen this before? This is 2 equations, 2 polynomials, and they have I will use here the 0, 0. Usually when people talk about multiplicity, they push everything to 0, 0, which in practice it's ridiculous, but for this, allow me to use this example. So the 0, 0 is a multiplicity 3 root, and what I mean by multiplicity structure here is that you give a list of derivatives that vanish at 0, 0 when you apply to this polynomial. So think of it that in the univariate case, when you have a univariate polynomial with multiple roots, you have a sequence of the point, the evaluation at the 0, 0 is 0, first derivative, second derivative, etc. In the multivariate case, there are directional derivatives. So it's while in a univariate case, you just have to know how many derivatives you take. Here, you can have these linear combinations of partial derivatives that vanish. And this is what we call to know the multiplicity structure. So basically, there is a vector space made out of these linear differentials that when you apply to the polynomials and when you evaluate at the point, so this is the notation I'm going to use here. So this partial I will be the derivative by x, partial derivative by xi, and evaluation at 0. So it returns a number. So when you apply this, then you get 0 on the original polynomial. Actually, you can apply on the whole ideal, and you will get 0. So it's called, and then you just want to have a basis of that vector space. So it's called either dual basis or sometimes called inverse system. It goes back in a second. I'll show you who it goes back. So when I say you would like to know the multiplicity structure of the root 2, you would like, I mean this, that you would like to compute this vector space or a basis of this vector space, of the dual basis. So the history goes back to Macaulay, and a lot of people work on this. So first I want to give you a method that computes this. So given the 2 polynomials and given the root, and in practice this works even if you have an approximation of this root, because you just have to do numerical null spaces of that matrix. So this goes back to Macaulay, this method actually, and called the dialytic method. So you set up a sequence of matrices. The first one is the degree 1, we call it Macaulay multiplicity matrix. You put in the columns corresponds to these linear derivative operators, and the rows with the polynomials, and you just evaluate them. So here, you just take the derivative and evaluate at 0, and you get this. And then you compute the kernel. The kernel the right kernel, is a linear combination of these derivatives that vanishes on f1 and f2, right? So you get these two elements. Then you go one further. Now you include the order. Oh, sorry, this is a 2 here. I don't know why I put it. These were the order 1. Now you include the order 2 derivations, and then you allow to multiply the polynomials by the variables. And again, you compute the kernel, and you get new elements of the dual basis. And then you do one more step. You compute the degree order 3 matrix, and if you don't get anything new, it's proven that you're done. You never find anything else. That's the dual basis. So that's what's called dialectic method. So it's really a kernel computation. But the disadvantage of this method that, again, if your order is high, the size of this matrix grows exponentially in the order. So the size of this matrix is basically the number of monomials in n variable of degree of the order. So for example, this system is a system that is used in the literature because the order is high. You can give general values for n variables, but it's always going to be exponential. So this method that I showed you for this system, for order 8, the Macaulay matrix will be a huge 1000 by whatever matrix. The method I'm going to show you will give the same answer by considering 4 16 times 16 strictly upper triangular matrices. So it's much smaller. And it's going to be polynomial in this number 16, it's just the multiplicity. It's polynomial in the multiplicity, doesn't depend on the order. And so here is the main idea. So the main idea is that if you had the dual basis, then the dual basis is as good as Grobner basis, basically. So this is what I will show you. So here we have again the same example, the same system, and you are interested in the primary ideal, right? The primary ideal at 0. And we don't have a Grobner basis, we don't know anything about it. But what I'm trying to convince you that if you know the dual basis, you can compute the normal form of any polynomial and the Grobner basis as well. Of the Q, we have a Grobner basis for the original system. Notice, one second, sorry. In this example, here, the original F1, F2 had this triple root plus an extra root. So it's not the same idea as the primary ideal at 0. So we don't know the equations of the primary ideal. Usually you don't know it. You have some polynomials, define lots of other roots, but you want to know locally what you think. So what I'm trying to convince you is that knowing the dual basis is as good as knowing a Grobner basis, because the normal form can be computed from the dual basis. So basically what you have to do is just to choose a so-called primal basis, just monomials that are orthogonal to your given dual basis. That can be done looking at the coefficients. And then this gives, so in the normal form of a polynomial will be a modulo the primary ideal will be a combination of the primal basis monomials, and the coefficients will be given by the dual element. And the proof is trivial, just really follows from orthogonality. So in this example, you can take the normal form of polynomials right? We don't know the primary idea. We know the dual basis, so we can take the normal form, and we know that the normal form minus the polynomial that you take the normal form of is in the ideal. So this way you can actually get a Gröbner basis. I don't know if this was understood. Not only a Gröbner basis, but what we will use is that you can get a Gröbner basis, but you can also get multiplication tables. So what are these multiplication tables? They are, so the multiplication map works in the factor ring here. So you take for any polynomial, so the multiplication by p is mu polynomial. P takes any polynomial q and take basically the normal form, but q times p modulo the primary ideal in this case. And here I wrote the transpose. So the rows of these matrices are normal forms of multiples. So when you write it down, of the basis elements, right? Fixed primal basis, these matrices will be normal forms of polynomials. So if you know the dual basis, you know normal forms, you can write these down, these matrices. But what we actually gonna do is the opposite. If you know the multiplication matrices, you can compute the dual basis. So we turn it all around and use the other way around. In this method, we will compute the multiplication matrices, and that will, because of this same property, you can read out the coefficients of the dual basis from the multiplication matrices. So that's the main idea. So, but this whole idea is that multiplication matrices and dual basis can be determined from each other. So what we will do is that we introduce, you don't know the multiplication matrices, we introduce parameters in them. So we assume that we know the primal basis, then you know the structure of these multiplication matrices. With some small assumption, you can assume they are all strictly upper triangular. They will be nilpotent. They will be nilpotent matrices, strictly upper triangular, and you will have some new parameters. And basically, what the equations you will get is the following, that these matrices have to commute with each other, and your input polynomials have to be zero when you substitute more or less these multiplication matrices into them. So this is more or less what we have. So starting from that system, you get a new system coming from the commutation of the multiplication matrices, and then when you substitute these multiplication matrices in the system, you have these new equations. And then you can solve that. And then you not only get the roots, but all the roots which has this fixed multiplication structure, and also the multiplication, the entries, the unknown entries of the multiplication matrices. So what we proved is that doing this always works, and it deflates in one step. This new system completely deflates the root. So this will always work. So basically what you need to know is nothing else but a primal basis that gives you the structure of the multiplication matrices, so you will know where you have to put zeros, ones, or new variables. You write up this new system that basically some of them will be the original. You see here, you can easily show that some of the equations in this system will be your original equations, and then some of them will have these new variables, and these new variables actually not always linear in them, but it comes from basically the size of this system is measurable to the multiplicity, like the size of this multiplication matrices. And it deflates in one step. And the number of new variables also, all polynomial. The size of this new system is all polynomial. You remember I mentioned that the deflation methods that we knew before, if you have to do multiple iterations, it will be exponential. This is always polynomial. And we can use it, so the coefficients here are all, if you start it with a rational system, it remains rational. There is no floating points involved. So you can use it again in the certification. So I think it's the last slide that you remember I mentioned this was the system where the order was really big, it exponentially grew. So this is how the dialectic approach will grow, and this is how the method I mentioned. So the last one you can do is n equal 4 with the dialectic, and I mean it's growing, but it doesn't grow that fast. So it's like significantly more doable. So with this method, there will be examples that are possible to do, but maybe not all, which was not before. So this is the end. So basically what I would like to just mention that there is a side where there are examples and computation, and then we are talking with mostly John Constance that we would like none of this, and we don't have a lot of idea how to deal with positive dimensional systems. So numerical homotopy gives sample points on those systems, but how do you give certifications for whatever property? Like for example, a question that raised that you have a system that over the complex number is positive dimensional, but over the real is 0 dimensional, like x squared plus y squared equals 0. How do you certify such a system? These methods, what I mentioned, will not work because you always work over complex. So this kind of, so we would like to extend similar methods to positive dimension. Thank you.
Thank you very much. More questions?
Is there any relation to Janet's evolutive?
I don't know too much about it. I think I've seen it, but you mean the last part, the
multipliers and...
I don't know. Yeah, I don't know. Sorry. I don't know too much about it.
Because Janet's work relies on Macaulay's things.
Mm-hmm.
So there is this Janet evolutive basis. I don't know if there's any relation that's not.
Yeah, no, I haven't seen it. I should probably look at it.
More questions? Let's go.
Is your differential, is your dual basis kind of CGG or FOSI? So the original F vanishes on the dual basis, is that correct?
Yeah, and the whole idea of multipliers also, yeah.
So,
Whether it's I don't know.
So it looks like the original F are first integrals of this dual basis.
Mm-hmm.
Right.
Mm-hmm. Yeah, and where this come up for me in other parts of my research is interpolation. So if you know, like Hermit kind of, multivariate Hermit kind of interpolations to give formulas similar to the Lagrange interpolation, you need to know these dual bases. Like basically in the univariate Hermit interpolation, you need to know the values of derivatives, and then if you want, it's a complicated formula, you can write up a complicated formula for in terms of your nodes and the derivatives and the function evaluation in those, how the Hermite interpolation works. And with Teresa and Carlos, we work on similar problem for the multivariate case, and these dual bases come up that it's good to know.
So it looks like a kind of reverse of finding first integral. You know the first integral, you want to find a differential equation.
Yeah, if you know the dual basis, you would hope to be able to. Well, this is how we just try. Maybe it's not even for the application, but just to give closed formula for this kind of interpolation problems. What we needed is to know dual basis of multivariate polynomial systems at points.
Is the dual basis unique in any way?
No, but the vector space, that space is.
The space is.
The space is, but the span is.
So the space will be all the differential equations, so to speak, that vanish.
That's how it's defined, exactly. And what's interesting is that there is this primal basis and dual basis, and for the primal basis, I mean, always you can find a basis that's made out of monomials. But for the dual basis, it's a very specific subspace that is, like most of the cases, made out of non-trivial linear combinations. So it's by the primal basis, you could think of that it corresponds to columns of a singular matrix where which span the column space, and you could most of the time choose the first ones, but not always. The dual basis is not like that. You really have something to compute. It's really kernel elements as we say in our matrix.
So do you have a complexity analysis of your nodes?
We just compute, not really complexity analysis, just the size of the number of variables and the number of equations. Yes, we do give the number of variables, but how to, you increase here. So basically the new variables, like here, the new variables are just those new parameters in the multiplication matrices, so they are bounded by how many new entries you have in the top of those matrices, and the new equations are also bounded by that number, more or less. Yeah, so
how do you solve for the mu's?
So this is actually what we trying to add to this paper, that it looks like that if you know the x variables, the mu's are, even though in this case it doesn't show as linear, but they depend linearly. So it's really hiddenly linear once you know the x variables. So they will depend on the. What I'm saying is not that. So basically, again, if you compute this rational representation, you will get something that's not linear in the x variables, but then you can express that mu3 is equal, and then it will be linear from the rest. It's usually that's the case in polynomial systems, but
so can you think of the system, if it is linear in the mu's?
Yeah.
Then can you think of this as a parametric system, linear parametric system on the mu's?
This one is actually
with the x ones as parameters.
Yes.
With the x as parameters.
Yes, this is, you can think of it as that gives you, so you can do this same thing and you would get so here, if you think of it, we put here numbers, but you could do this symbolically, just writing down what's the derivative of f and then using x's. Then this would give a system that's not linear in the x variables, but linear in the mu's, but it's just too big compared to what's ours. It can be exponentially big, but linear in the mu's. Ours is polynomial size system, but not linear anymore in the mu's. But we would like to show that it's easy to get a linear system from that. I don't know yet how to do it, but I think on Maple we did 3 examples and it looked like it's true. So it's just. So that's.
I might be tempted to try another method of, when you're looking at the overdetermined systems, to find a nearby system which has a root,
Mm-hmm.
and then to see if that plane that's determined can have a rational form. And you have a rational,
And how would you do that?
I don't know, is that not some Diophantine inequality, I suppose, like you use to get a lower bound on
But I think you get back to, so that's not enough to show that it has a rational point. You have to have that it has 0 is a root. So the perturbation equals 0 is a root, right? That's what you want to show, right? So you perturb your overdetermined system, but you want to show that the original system has a root. So you have a parametric system, and you want to show that 0 is a root. So this, I thought of it. It's, you can turn it again to a new overdetermined system that want to show that the last coordinate is 0 or something of that sort in the root. So yeah, I think I don't know, there is no way around it, that at one point you have to compute some object that is computable and rational and verifiable, because eventually, I don't know. Yeah, I think that's what you would end up again, another overdetermined system that you have to solve or certify.
More questions, comments? No, I guess not. No. Thank you very much.
Thank you.